year seminar. Today we're honored to have with us Jennifer McIntosh. So Jennifer did her PhD in 2004 in the University of Michigan. Then she did a postdoc at Johns Hopkins University. And since 2006, she's been faculty at the University of Arizona, the only Department of Hydrology and Water Resources, which is the only one in the country, in a joint appointment with the geoscience at the University of Arizona. And she's very young, but have a very long record already of kind of impressive achievement. And we are very honored to have her here. Thank you for coming.
Thank you, Avner. Thanks for hosting me. Had a great day visiting with faculty and students, so thanks for having me. Today, I'm going to talk about my past research on climate change, both on groundwater and energy resources. This is meant to be pretty informal, so if you have any questions, feel free to stop me and ask. So just before I get started, some funding sources. So my research, both from the energy side, gets a lot of funding from places like the American Chemical Society, Petroleum Research Fund, the USGS, Geological Survey of Canada. The groundwater side of my work gets funding from the Nuclear Waste Management Organization of Canada. I'll talk about that because they're planning to put radioactive waste in saline aquifers that were glaciated, and I have funding from NSF. So the work I'm going to talk about today, I have 3 graduate students, a PhD student, and 2 master's students who are working on new aspects of this research, and then a long list of past collaborators that have greatly aided this research. So I'm going to organize my talk around 2 central research questions. The first one is, how did past climate change, such as Pleistocene glaciation, impact recharge and storage of freshwater resources in continental aquifers? The second part of my talk will be on what effect did subglacial recharge have on the generation of natural gas, such as methane, in organic-rich shales and coal beds. And then we'll summarize and send you away with some conclusions. So this is a picture showing the northern hemisphere at the last glacial maximum, about 18,000 years ago, versus today. So over the past 2 million years of Earth's history, most of it's been dominated by continental ice sheets. This is the Laurentide ice sheet shown here, the Cordilleran ice sheet. As these ice sheets grew, they stored huge volumes of fresh water on the continents. So the Laurentide ice sheet, for example, contained over 20 million kilometers cubed of fresh water. These ice sheets accumulated in the Hudson Bay, went as far south as the Ohio River Valley, and advanced and retreated about 20 times. So it's long been recognized that as these ice sheets melted, they dramatically changed the Earth's surface landscape. So you had freshwater discharge through surface drainages out to the oceans, which affected thermohaline convection in the oceans. But it's only been recently that hydrologists have recognized that a significant portion of that glacial meltwater actually recharged into the subsurface and has been stored on the continents, primarily within sedimentary basins and fractured bedrock aquifers. So this is a map showing the Laurentide ice sheet at the last glacial maximum. The blue is the ice sheet, and the contours are the thickness. So this ice sheet went from less than 1 kilometer at its margin to over 4 kilometers in thickness. The area shown in pink are regions of permafrost, which actually inhibited freshwater recharge. And then the orange is showing the major, mostly Paleozoic basins in North America. And it was the juxtaposition of these thick ice sheets with these sedimentary aquifers that caused freshwater recharge and storage of this important groundwater resource on the continents. Interestingly enough, at the last glacial maximum, sea level was low and you had continental aquifers exposed off the shelves, and you did have subglacial recharge into those aquifers. So today I'm mostly going to talk about my work that's been done in the Michigan and the Illinois basin, but there's a lot of other case studies in North America as well as Europe about subglacial recharge into aquifers. So just to kind of give you a visual, this is put together showing the Laurentide ice sheet, and this is the subglacial meltwater rate. What I think is interesting is the yellow is the area where the ice sheet was actively melting, so it's towards the margin of the ice sheet. And remembering that beneath that ice sheet were these sedimentary aquifers. This is a picture showing permafrost thickness at the last glacial maximum. That becomes important because permafrost is a layer of ice. And so you may have had glacial melting on top of the permafrost, but that was a very low permeability units. So in areas where it was covered by permafrost, you have hiatuses in recharge into aquifers. So as I mentioned, most of my research has been done in the Great Lakes area in two Paleozoic basins, the Illinois Basin and the Michigan Basin shown here. So the hydrogeology of these three basins actually is pretty similar. So if you were to go through the strat section, it's very similar. One of the major differences is the presence of salts in a couple of these basins and then saline fluids. So the original salinity within these basins affected their response to glacial loading and how much fresh water was able to recharge into the margins of these basins. So for example, this is a cross-section of the Illinois Basin. The Illinois Basin, as it formed, was not as restrictive as the Michigan Basin, so you didn't form evaporites. Where the Michigan Basin, there were times during the Silurian where you built up huge salt deposits, so over a kilometer thick salt within the Silurian section. So you have a much more saline brines in the Michigan and the Appalachian Basin. You can see that in a salinity profile shown here. These basins go down over 4 kilometers, and this is the maximum salinity with depth. So you see the Michigan Basin is almost up to 400,000 milligrams per liter TDS. These are some of the most saline brines in the Earth's crust. Illinois Basin is about half the salinity. So that plays a role when you talk about forcing fresh water into these basins. You're able to get a lot deeper penetration in the Illinois Basin than the Michigan Basin. One final thing to mention, glaciation was really key for hydrology of this mid-continent area. So if you've ever been to the state of Michigan, it's pretty flat. I mean, I don't know, compared to North Carolina, maybe about the same, but all of a sudden put a kilometer thick ice sheet on top of this area and it completely changed the hydrology. So some of the first evidence of subglacial recharge into these sedimentary basins was done by simply mapping the salinity or chloride concentration of groundwaters and then deeper saline fluids. You sample groundwaters through domestic drinking water wells, saline fluids through deep oil and gas wells. So this is salinity map of fluids within the Cambrian Ordovician, both sandstones and carbonate aquifers. So this includes the Mount Simon as well as the Jordan sandstone. And Don Siegel was the first person to kind of put the salinity map together, and what he showed is that there's this plume of anomalously low salinity waters that seem to correspond with the Des Moines lobe of the Laurentide ice sheet. As we would expect that salinity would probably march along and become simply more saline with depth, but yet you see this plug of low salinity water deep into the Illinois Basin. Most of my research has been done on the Silurian Devonian age carbonate, which is a major regional aquifer system, important for a lot of metropolitan areas. And what you can see is that you also find this plume of anomalously low salinity water deep into the Illinois Basin. And what I think is curious is the fact that you see this kind of north to south gradient in salinity. So this seems to correspond with the lobe of the Laurentide ice sheet that came down in this direction. Okay, so these low salinity... Sure, I'm going to show you that in a second, but this is about 1 kilometer, at least down to here. So low salinity is our first piece of evidence of subglacial recharge. If you look at it versus depth, what you can see is that some studies on basinal brines, just because of diffusional profiles, would say that salinity should just simply increase with depth along a linear trend, but what we see is depressed salinities to a significant depth, so up to about 1 kilometer. In both of these regional aquifers. And I don't think I mentioned this. This is the major aquifer system for Chicago, Detroit, so a lot of fossil groundwater coming from glacial recharge. So how do we know that these low salinity waters weren't simply meteoric precipitation and were really, in fact, melting of the ice sheet? We turn to stable isotopes, so water, H2O. We look at the masses of hydrogen and oxygen. They're fractionated based in part on temperature and source of water. So this is a plot of the hydrogen isotope value versus the oxygen isotope value of waters within these two regional aquifer systems. The waters that plot along the global meteoric water line are primarily from drinking water wells, okay? Where the waters that deviate from the line are primarily saline brines. And this is typical of a pattern of evaporated paleo seawater. So what's interesting is that you always want to compare this to modern precipitation. So I've highlighted on here the range of values for modern precipitation. And what you can see is that dilute groundwater in both of these aquifers have oxygen isotope values that are significantly depleted. we have a couple records of what the Laurentide ice sheet oxygen isotope value could have been from a couple different paleoarchives. Some of the best ones are from pore waters from Glacial Lake Agassiz up in Canada. They're about minus 25 per mil, delta 18O. There's wood cellulose studies. There's one done in Ontario, Canada, close to here. There's some speleothem studies from cave deposits. So we've tried to constrain what we think the ice sheet value was, and it was somewhere between about minus 12 to about minus 25 per mil. So clearly there's mixing of glacial meltwater with groundwater that's more positive in these regional aquifers. So this led to a conceptual model that I put together of the effects of glaciation on recharge. So this is what northern Michigan probably looked like about 12,600 years ago. So just to put it in perspective, this is the northern margin of the Michigan Basin. This is Mackinac Island. This is the upper peninsula of Michigan, the lower peninsula. So the ice sheet had advanced, and here it was 12,000 years ago. And we think that it was wet. We know it was wet-based, and that you had subglacial recharge. We think that these carbonate aquifer systems were a drain for subglacial recharge because they're highly permeable. And then that water discharged at the toe of the ice sheet. And here's what it looks like today. Today, because the area is relatively flat, most of our topography are glacial sediments or glacial moraines. And most of the groundwater recharges at these topographic highs and then discharges out to the Great Lakes. So you have very little penetration of modern groundwater into these regional aquifers. One of the reasons for that is that there's remnant glacial lakebed clays that are here. And so they're impermeable caps. And so you've stored late Pleistocene groundwater pretty close to the surface in these regional aquifers. And as I said, that's an important drinking water source for some cities like Chicago. So let me back up. One tracer that we have that these carbonate aquifers were the major drain for subglacial recharge is the fact that these aquifers contain salts. Okay? So there's salts within the Silurian carbonates and some salts within the Devonian, where there's no salts from the Antrim Shale through Mississippian shales. So we can tell by looking at chloride to bromide ratios that all this fresh water coming from melting beneath the ice sheet recharged in the carbonates and dissolved salts, because we see really elevated chloride to bromide ratios. Okay, so just pay attention to the blue here. This is water within the Antrim Shale unit, and the red is showing deep brine within the basin that came from evaporated paleo seawater. So just what I want you to notice is the fact that the chloride to bromide ratios are very elevated, and this is indicative of halite dissolution. So halite sodium chloride, you dissolve that, you get very little bromide. If we look at the oxygen isotope value of those waters, once again to try to get at the source of this freshwater recharge, we can see a mixing trend or a dilution trend between saline brine that was remnant in the basin and these subglacial freshwater recharge waters. And it seems to be a mix of modern water and glacial water in terms of its oxygen isotope value. So in order to constrain the age of the water, we have done some carbon-14 age dating, which is problematic in a carbonate aquifer because it contains calcium carbonate, dissolves in water, and adds a bunch of dead carbon to the water. So if you back out the addition of dead carbon, the ages range from about 7,000 to over 30,000 years old. So it's certainly within the range of the last glacial maximum. So I'm showing you this slide because I did a mass balance calculation. I was curious how much salt could have come from glacial recharge and dissolution of these halite beds. If you just account for the excess chloride, you figure that of the salinity within these carbonate aquifers, over 50 to 80% of it came from dissolution of the salt. If you look at bromide, you can figure out how much dilution of those brines could have occurred. So the take-home message is that you've had over 80% of that water, saline brine, replaced by subglacial recharge and dissolution of salt. So you all of a sudden have this Paleozoic brine replaced by a Pleistocene sodium chloride water, which I think is interesting. So I just told you a little bit about subglacial recharge into carbonate aquifers in the Michigan Basin. I'm showing you this map because these carbonate aquifers are extensive throughout all of North America. So it's the old margin of the craton, you know, the Canadian Shield. It's rimmed by these Paleozoic carbonates. And as I hopefully convinced you. I think that they were a major area of focused subglacial discharge into the Michigan Basin. It's also been shown over in the Williston Basin and the Western Canada Sedimentary Basin to be the same case. So these were important drainages for subglacial recharge. One thing that's interesting from this map is that the red is showing esker systems. So, and beneath that in pink are crystalline rocks. So the idea is that the ice sheet accumulated in the Hudson Bay. It moved over these crystalline bedrock that's relatively impermeable. And so you may have been generating subglacial meltwaters, but those meltwaters couldn't infiltrate into the subsurface. And so it drained through esker systems. But as soon as the ice sheet hit these permeable carbonate aquifers, that water was able to infiltrate and the eskers disappear. So this is a hypothesis from some of Steve Grasby's work. So we've recently tried to calculate the volume of the Laurentide ice sheet meltwater that may be stored on the continents. And this is still pretty preliminary work. So there's a few case studies like what I've shown you of my work in the Michigan Basin where we've tried to quantify how much glacial recharge could have been stored in these aquifers, but there may be other places that haven't been investigated that contain glacial meltwater. So given that, a minimum estimate we came up with is about 0.3% of the ice sheet. There's another study done by Lemieux that was all based on modeling, and they came up with 5 to 10%. So like I said, a lot more work needs to be done, but we're starting to try to quantify. And in my mind, it's a significant amount of fresh water that's paleo in age from melting of the ice sheets.
What's that number again? 5 to 10%? What's that?
That's the amount of the Laurentide ice sheet. So that 20 million kilometers cubed of fresh water in the ice sheet, how much of it was stored on the continents after melting? So the rest of it went out to the oceans. Okay. So to try to visualize some of these processes and test my hypothesis about these carbonate aquifers being a drain for glacial meltwater, I did some groundwater modeling. And I'm going to show you the results because I think it's a good illustration. So I constructed a transient, which just means a moving model, in 2 dimensions of the northern half of the Michigan Basin. And I asked the question, how much freshwater recharge would you get under modern topography conditions? Let's just let it rain on the Michigan Basin for 2 million years and see how deep of penetration versus loading with a kilometer thick ice sheet. So once again, this is half of the Michigan Basin. So my model, I just chose to do the northern half because the center of the basin is an area of regional discharge. The basin's 4 kilometers in thickness. This is the Cambrian Mount Simon aquifer, which I know some of you work on. Here are the Devonian carbonate aquifers in blue. And these hot pink units, these are carbonates that contain this bedded salt, so it's relatively impermeable. And then on top, those are our glacial sediments. Okay, this is an initial salinity gradient. So in order to do any kind of modeling, and I'm going to trace salinity, I had to make an assumption about what the salinity in the basin looked like before you had any glacial recharge. So I just took a maximum case scenario and I said, let's look at the maximum salinity with depth of the Michigan Basin today and impose that on the basin. And I'm showing you this because I want to impress upon you how saline the brines are in the Michigan Basin. So seawater's 35 grams per liter total dissolved salts. And in the Michigan Basin, we quickly get up to 10 times the salinity of seawater. So it's basically a bowl full of salt and saline brine. So I'm now going to pass through this transient model that I constructed of ice sheet loading to show you what impact subglacial recharge would have on the salinity gradient in the Michigan Basin. So you're tracking 2 things. The first one is hydraulic head, which is simply the pressure of the ice sheet. So at time 0, this is 500 years actually into glaciation. So this direction is the Canadian Shield. The Laurentide ice sheet's coming this way, all the way out to the Ohio River Valley for the glacial maximum and then retreats. So you'll see those colors changing as the ice sheet's advancing. And what we do is we take the density of the ice, which is about 90% of fresh water. We assume that there's an exponential gradient and hydraulic head, and that's how we get the effects of the ice sheet on groundwater. So this is showing the total dissolved solids or the salinity. So already at 500 years into ice advance, you can start to see recharge of fresh water. sweeping out some of those saline brines. So I'm just going to march through this. And as I said, the ice sheet's advancing across the Michigan Basin out to the last glacial maximum. I think I'll stop at the glacial maximum. So it took about 8,500 years for it to go from the Upper Peninsula of Michigan all the way out to the Ohio River Valley. And now it's covered the entire Michigan Basin. And you can see focused recharge into these more permeable carbonate aquifers. And in the shallowest aquifers, it's completely flush saline brine. So now the ice sheet's retreating, and we're still getting recharge of subglacial meltwaters into the basin. Sorry, this is kind of low tech. I could have this animated, but I'm the animator. All right. So a couple of things to take note of. Once again, because I assign high permeabilities to these carbonate aquifers, you do see flushing and dilution of these saline brines. This is a zone of fresh drinking water. One thing that's important to notice is that this model didn't incorporate solute reactions. So I mentioned that these glacial meltwaters recharged in the carbonates and they dissolved a lot of salt. So these are actually maximum freshwater extent. So the salinity is probably a lot higher because of salt dissolution. And finally, that we do maintain some of these anomalous pore pressures because of glacial loading. So we're still seeing these basin responding to the last glacial maximum. And this freshwater saltwater interface is probably rebounding slowly. So this model that I did was one of the first models of the impacts of glaciation on groundwater. There's been a lot of models done on ice sheets and surface hydrology, but not on subsurface. And it was relatively low tech. There's a lot of things that I would want to incorporate in that model and that we're doing now. So for example, I didn't include permafrost, and I said that was probably really important, that caused hiatuses in recharge. I didn't include the effects of mechanical loading of the ice sheet on the rocks. So we know that there was some dilation of fractures because you loaded, increased pressure, and then the ice sheet left, and you could have dilated fractures. So we're doing some of those things. But I'm going to end the modeling with a conceptual model that we put together. Kind of hopefully gives you a picture of the effects of glaciation on groundwater. So this is showing a generic basin at the last glacial maximum. You generate excess pore pressure because of loading of the ice sheet. If you have permafrost at the toe of the ice sheet, you get deeper penetration of groundwater. The ice sheet's retreating, and we've got proglacial lakes. So you could have had infiltration because of these high stand lakes. And then finally, here we are today at the Holocene, where most of this groundwater circulation is really close to the surface, and you maintain these fossil groundwaters at depth.
On the top figure, what's the excess pore pressure? That's the orange.
Yeah. Right. If you're interested, we wrote a review paper in Reviews of Geophysics on Pleistocene hydrology that these figures come from. So I just found this figure. I thought this was interesting. This is so I asked the question, is there a modern ice sheet that we could look at today and see these same effects? Well, if we go to Greenland, this is data coming from Greenland, and there it's from an ODP cruise, and they have pore waters from coastal aquifers off of Greenland. What you can see is that the oxygen isotope values, there's a mixing trend between low chloride, which would be the subglacial meltwater, and ambient groundwater in the aquifer. So we do have a modern day analogy to what I'm talking about. And I wanted to bring this figure in because, I am pretty North America centric because all of my research has been in North America, but these same processes were happening in Europe. This is a picture of Europe at the last glacial maximum. The blue is the ice sheet cover, and the black is the southern extent of permafrost. So what's interesting is a lot of the aquifers in Europe were actually covered by permafrost rather than by an ice sheet. And so you see hiatuses in recharge during those periods. The pink are sedimentary basins. So I'm just going to show you one data set from a study in Europe, because I think it nicely shows what I think are important tracers for groundwater studies of understanding paleoclimate change. So really, I've shown you some data from my work on stable isotopes, which are useful, but not always conclusive, because there are some data sets where the oxygen isotope values are actually more enriched than modern precipitation. So you scratch your head and think, well, this couldn't have been glacial meltwater. What was it? So we try to couple it to some kind of age indicator. In this case, this is a study of the Midlands Triassic Sandstone Aquifer in the UK. Mike Edmonds was the lead author, and showing groundwater age within this aquifer versus stable isotopes and recharge temperature. So another tool that we use is noble gases. So noble gases come from the atmosphere in part. They're dissolved in groundwater based on the temperature in the recharge zone. So if you end up with higher concentration of gases in your water than you'd predict with modern temperature, you could say that water was recharged when it was colder, is one way we use it. So if you put all these things together, what you can see is that in this aquifer, starting from about 35,000 to about 20,000 years ago, groundwater is recharged under a much colder climate, and the oxygen hydrogen isotope values of that groundwater was more depleted than it is today. And by getting a pretty high resolution of groundwaters along a flow path, you're able to see that between about 20 and 10,000 years ago, there was a hiatus in recharge. And if you look at the permafrost extent, you can tell it's probably because this area was covered by permafrost. And you see this all across Europe. Okay. So any questions on the subglacial part? Because I'm going to change gears a little bit. Okay.
Ask a question. This is about a cross-section much earlier in the talk, but you have, under the ice sheet, you have a groundwater flow line that is originating in the recharge area, which is the carbonate aquifer, and going right through a shale unit. And so is that a pressure argument as to why that's not functioning as a confining unit under, or what's causing that to happen? Because
Yeah.
it seems like for like a question of water rock interactions, that would be a really important issue as to.
Yeah, that's a great
gone
question.
through a big shale.
Right. So part of it is how we draw geologic cross-sections. So as you see, if you take the entire Michigan Basin and you put it true to scale, it's thinner than a sheet of paper because it's 4 kilometers in depth and hundreds of kilometers in spatial extent. So the way that I drew that, it looked like you had flow lines that went, to the center of the earth and then came back up through the shale, but really it's more horizontal flow. So it's not unrealistic. And then the other aspect is the shales are actually pretty fractured. And we can tell from the water chemistry in the shale that it is receiving recharge from the carbonates. So we know they're interacting, but it's a good question. Okay, so now I want to shift gears and talk about energy resources. So I can hopefully convince you there's a connection between Pleistocene glaciation and generation of natural gas. So this is back to the mid-continent area. This is showing the 3 basins again, but now what I'm showing is Upper Devonian shales. So the subcrop of these shales is shown in black here. So basically all 3 basins contain this very organic rich shale that's over 100 feet in thickness. It's the major source rock for hydrocarbons in these basins. Well, these shales received freshwater recharge during times of Pleistocene glaciation. And if you look at the origin of natural gas within these shales, you can see that there's 2 types of gas. So most conventional hydrocarbons are generated when organic rich rocks are heated up at high temperature and high pressure, usually at the center of the basins at great depths. And so that's where we generate thermogenic gas. And thermogenic gas contains methane, ethane, propane, all these higher chain hydrocarbons. So it's got a certain chemical signature. Okay. Where microbial gas is natural gas, methane and CO2, that's generated by microorganisms. Okay, so these microorganisms eat the organic rich shale or coals and produce natural gas. Okay, this is a phenomenon that could have occurred from the time that that shale was deposited up until the present. Okay, and we think a lot of the natural gas along the shallow margins of these basins was generated within the last glacial maximum. So I'm showing in orange here is the maximum extent of glaciation. So the ice sheet covered all the way down to this region. The dotted line is the last glacial maximum, so the ice sheet didn't make it as far south. And then what you can see, I've done a lot of research in the Michigan Basin and in the Illinois Basin on the origin of natural gas. And from that work, I've outlined areas of dominantly microbial gas versus thermogenic gas. And I'm going to show you data in a second, hopefully linking the two, why I think that these microbial gas deposits were stimulated by subglacial recharge. And I should mention this. I have a PhD student who's now working in the Appalachian Basin. It's a really huge Upper Devonian shale play, and the question marks mean that we don't know a lot. So, okay, so a little bit about the hydrogeology. So these Silurian Devonian carbonates that we're discussing is probably a drain of subglacial recharge into the basins. These are what are underlying these organic rich shales. Okay, so I think that fresh water came into these carbonates and penetrated into the overlying fractured shales. There's another source rock in the Illinois Basin, and that's Pennsylvania age coals. So the coal beds are shown in blue here, and they're also adjacent to a regional aquifer. So showing you a cross-section of the Illinois Basin this time. So pretty similar geology to the Michigan Basin. What's missing, I mentioned, are these bedded evaporite deposits. So the salinity is much lower. This is the New Albany Shale, which is Upper Devonian in age. I'm going to show you data from that. The Pennsylvania coals are shown there. Show you data from that. And then there's another organic rich unit called the McIntosh Shale. It's Upper Ordovician in age. It's also called the Utica Shale in other areas. And it could potentially also be a source rock. So the Laurentide ice sheet covered the basin, almost all of it, in its maximum extent. And at the last glacial maximum, just covered the northern margin. So this is my conceptual model of the Illinois Basin at the last glacial maximum. See, the ice sheet covered the full basin, well, at least this part of it, not showing the whole basin. You had subglacial discharge and recharge of those waters preferentially into these more permeable aquifers and migrating up into the shales and coals. Yeah, sorry, I think I made that confusing. That was the Illinoisan glacial limit, so that was the full extent. Here we are at the last glacial maximum where it only covered the northern margin. And so the coals, for example, were probably recharged by Pleistocene precipitation rather than glacial meltwater. And finally, here we are today, where most of groundwater circulation is just really localized to the shallow subsurface. So if we look at, I showed you in a spatial map where you find zones of thermogenic gas versus microbial gas. This is just looking at it in cross-section. Most of the microbial gas is located along the shallow margin of the basin. Thermogenic gas at depth, there's obviously a mixing zone between the two. And within the Pennsylvania coals, it's all microbial in origin. So how do microbes generate natural gas? Well, this is showing the breakdown of coal. Could be the same for black shale. So you take basically long chain complex hydrocarbons. You have a community of microorganisms. Some of them break down the complex organic matter into smaller food sources that then the methanogens can finally use to make methane and CO2. So some of those shorter chain carbon sources that the methanogens can use are things like acetate, amino acids, CO2, hydrogen. So it's finally broken down to the three things that methanogens use: acetate, hydrogen, and CO2. They're then broken down into methane and CO2, okay, which we produce from these wells. What's important is that there's two different pathways that methanogens use to make natural gas. One is through using acetate to produce methane. The other is reducing CO2. The reason why it's important, I mean, who cares, they both make natural gas, is the fact that if we want to try to stimulate this process, we need to know what is it that the methanogens are utilizing. Is it acetate, in which case we add more acetate, or is it CO2 and hydrogen? So one way that we try to distinguish those mechanisms of methane generation is through using isotope tracers again. So methanogens take hydrogen from water in part and hydrogen from organic matter and produce methane. A CO2 reducing methanogen takes a different proportion of hydrogen from organic matter and water than does an acetate fermenting methanogen. And so we can use the fractionation of hydrogen isotopes between methane and water to be able to distinguish the major pathway. Okay, so these are coupled analyses of water, produced waters from a gas well and methane. I'm going to show you a couple different plots using this data. So just to describe it, there's methane within 3 different units in the Illinois Basin. These Upper Devonian shales, shown in purple, the Pennsylvania coal beds shown in blue. And then in glacial drift, there's also methane, because methanogens can live in any anoxic environment where there's no sulfate, and they just need an organic carbon source. So in some glacial drift deposits, there's enough disseminated carbon. They can make methane. Well, plotting it up this way, you can see that most of the data falls close to the CO2 reduction line. So it seems like CO2 reduction is probably the dominant pathway for making methane in the Illinois Basin. Although, make a caveat, when we've done this similar study in the Antrim Shale in the Michigan Basin, we've coupled it to microbiology. And when we do that, we see the presence of both acetate fermenting methanogens as well as CO2 reducers. So it seems to be a little more complicated than what I'm showing you here. So one other way that we try to distinguish the pathways is through coupling CO2 and methane isotopes. So I mentioned the microbes produce both CO2 and methane. Acetate fermenting methanogens have a different fractionation factor than CO2 reducers. So we plot it up like this. We see that once again, all of the data from the Illinois Basin plots along a line that's been indicative of CO2 reduction. So that seems to be the dominant pathway for making methane in the Illinois Basin. If you look at thermogenic gas, most thermogenic gas has a carbon isotope value that's much more positive. And the source of CO2 is simply from the organic matter, and it hasn't been fractionated. Okay, so that's one way to distinguish thermogenic from biogenic gas. There's another interesting trend on this plot. So you can see that you go from glacial drift methane to coal beds to the New Albany Shale. And I think this is representative of simple Rayleigh fractionation. So these microbes have a pool of CO2, and the first CO2 that's generated is close to the carbon isotope value of the original organic matter. Well, as methanogens remove lighter isotopes from that CO2 pool, the CO2 pool becomes heavier. And so then the next methane that you generate is also heavier. So I think we're marching along this line through Rayleigh fractionation. And I think it's in part related to the hydrology. So if you look at it versus depth, you can see that the carbon isotope value becomes increasingly more positive. So I think we're going from a more open system, isotopic system, to a more closed system. One thing that's important is that now all of a sudden at depth, the New Albany Shale biogenic gas has the same carbon isotope value as the thermogenic gas from the center of the basin. The reason why that's important is that often people will just look at the carbon isotope value of methane to distinguish thermogenic from biogenic gas. So to kind of summarize those results and put it back in context of the hydrology, I've shown you that the lowest isotope values are found in the glacial drift, pretty rapid flushing of groundwater, new generation of CO2, an open isotopic system. We go to the Pennsylvania coals, they're a little bit deeper, more of that CO2 pool has been depleted. And finally, the deep New Albany Shale, where I think methane's been generated for a long period of time, and that CO2 pool has been greatly depleted. So right now, we have an ongoing NSF project that, looking at groundwater age tracers within these deep shale and the shallow coals. We're looking at things like organic geochemistry to better understand how these microbes are breaking down organic carbon to produce methane, what some of their different intermediate food sources might be. We're doing DNA and RNA studies. The first one's done on these shales and coals in the basin. Try to understand how's the microbial community within a deep shale different from a shallow terrestrial coal bed. And finally, doing numerical modeling to try to look once again at the impacts of glacial loading on recharge. So just a couple final results on the natural gas that I think is interesting. So one of the dominant controls on how deep you find microbial activity in the Illinois Basin, I think, is salinity. So there's a couple different factors that affect microbial activity deep within the subsurface. So there's temperature. So at some point you fry the microbes, but it seems to be about 100 to 120 degrees C, where most of these waters are up to maybe 30 degrees C. So temperature is not a factor. Sulfate concentration is not a factor because there's no sulfate. It's all been reduced. So that leaves things like salinity, transport of nutrients, available organic carbon. Okay, so we're looking at all those factors. And this is showing the salinity within the New Albany Shale. So this is showing that we go from low salinity to high salinity, and that there's this, once again, this weird tongue of low salinity water. And I showed you the same pattern in the underlying carbonates. So this is evidence that you had freshwater recharge into the carbonates, and it's communicating with these shales on top. And you find biogenic gas only in these areas of lower salinity water. And so deeper in the basin, it's all thermogenic in origin. In the Pennsylvania coal beds, salinity is much lower than the New Albany Shale. So these are some initial results that we've got on groundwater age dating. And so we say we've got this plume of low salinity water. What's it sourced from, and what was the timing of recharge? So we measured carbon-14 within the water. Well, I mentioned there's a lot of problems with carbon-14 age dating of carbonates. We've got an added problem of microbial activity. Microbes eat dead carbon. These Devonian shales put dissolved inorganic carbon into the water, which then makes the water look much older. Okay, so we'd have to back out those things. But I think the fact that we've got detectable active carbon within the New Albany Shale at up to about 1 kilometer depth tells me that those waters are younger than 50,000 years old, which to me is interesting because it means that this basin has received recharge at least within the last 50,000 years, and that that fresh water is penetrated up to 1 kilometer.
Is there no other source of C14 radioactive decay?
Yeah, it's all cosmogenic in origin.
Really? No.
Yeah. But we really want to couple this to a better age tracer. So we're working with Chris Ballantyne in the UK to do noble gases. So we're going to be able to get a much higher resolution groundwater ages. For noble gases, so helium-4 for doing age dating. We can't do paleo temperature, unfortunately. I mean, I think those studies are really interesting to couple to things like carbon-14, but that's based on solubility of gas, and you sample a natural gas well, and it's spurting water out. So you've already lost a lot of the dissolved gases. So we can simply get age, not paleo temperature. Okay, so I showed you a little bit about natural gas in the Illinois basin. The same phenomena is occurring throughout the United States and the world. So this is a map showing coal bed methane and shale gas plays. So of all the natural gas resources in the United States, 20% of that natural gas resource is generated by microorganisms. And it's actively being generated, so we can culture these microbes. So we know that some of the methane was generated in the geologic past, but some of it's still continuing to be generated by active microbial communities today. So that leads us to a motivating question, which is, can the microbial generation of methane be enhanced on human timescales? So this is something that my research group is ultimately moving towards, and the USGS has a 10-year goal that in 10 years we're planning to do a pilot field study where we'd like to be able to stimulate methanogenesis. So the idea is to either go to a location where we know there's known microbial activity and somehow stimulate it, or go to a place where the geologic conditions seem ideal but there's no microbial activity and inject microorganisms. And it's not such a far-fetched idea because there's a company that's doing this for profit called Luca Technologies out of Colorado. The other big picture question that my research is kind of motivated by is that these black shales and coal beds are the same targeted sites that people are talking about injecting CO2 into the subsurface for long-term storage of anthropogenic CO2. So we're talking about sequestering CO2 into saline aquifers, which I showed you some examples of those, coal beds and black shales. And the reason for that is it's a different trapping mechanism. CO2 is strongly absorbed onto organic matter, and it displaces methane. Okay? And so oil and gas companies have been doing this for a long time, injecting CO2 into coals and shales to get more methane off. But one of the questions that I haven't seen addressed in the literature is what impact would injection of CO2 have on these microbial communities living within these coal beds and black shales? I showed you evidence that these microbes generate methane through reducing CO2 in addition to hydrogen. So I want to ask the question, could we actually generate more methane through CO2 sequestration? So to end with some conclusions, I've shown you evidence that if you couple groundwater geochemistry with hydrologic modeling, It looks to me like Pleistocene glaciation had a profound effect on subsurface flow patterns, recharge rates, distribution of fresh water in confined aquifer systems in sedimentary basins. Showed you some examples from the Michigan and Illinois basin, but this is a global phenomenon. I showed you some fluid and gas geochemistry from organic rich shales and coal beds in the Illinois basin that indicate a lot of this natural gas is generated by microorganisms, and there seems to be a connection with subglacial recharge and the stimulation of methanogenesis. And finally, these results have implications for the sustainability of water and energy resources, as well as the long-term storage of anthropogenic waste, such as CO2, and also radionuclides. So we're funded right now by the Nuclear Waste Management Organization of Canada because they're planning to put low and mid-level radioactive waste into saline aquifers that were glaciated in the Pleistocene and could be glaciated in the future. And you think about the half-life of radionuclides, these things are going to be around in terms of the next glacial period. So they're interested in our work in terms of how deep these fresh waters might penetrate into potential sequestration sites for radioactive waste. So thank you. I end with a picture of Arizona. So.
So do you think that this CO2 fertilization of microbial methane generation, what happens to the methane that's released or is it trapped?
Good question. So probably both. So it's generated, and then that's excess CO2 is probably trapped on the sites that the methane was located, and so it probably sweeps methane out. So you get an energy resource or you get a greenhouse gas, the way that you look at it.
Would it offset the greenhouse gas potential since methane is such a stronger greenhouse gas? Would it offset the benefit of injecting it?
Well, you'd have to burn it on site and then re-inject the CO2 for it to be a closed energy loop. Good question, though. That's a good question. I don't think we really have any idea, if we know that there's this feedback because methanogens naturally convert CO2 that's present in the subsurface to make methane. So in my mind, the big question is at what rates, could you generate new methane? And it's the same process that happens in landfills. It's just really slow in the subsurface. So we'd have to stimulate it somehow and then trap the methane. But that's kind of why coal beds and black shales are unique, is it's both the source as well as the reservoir for natural gas, because it's stored onto the organic matter. Good question. The answer is yes, all over the place. So, and it's not just in areas that were glaciated. So I'll give you some examples in glaciated areas. So Chicago has greatly depleted their Cambrian-Ordovician aquifer, and most of that water was Pleistocene meltwater. Off the coast, so the coastal aquifers in Europe as well as in North America, it's paleo water. So there's been a lot of work done by my colleague Mark Person off of Nantucket, New Jersey, all these coastal plain aquifers. And I say you don't have to be in a glaciated area because, so for example, the desert southwest or southeast of the United States, it wasn't covered by an ice sheet, but it was at least 4 to 5 degrees colder and wetter. So in Tucson, most of our groundwater is fossil groundwater, probably Pleistocene in age. Right, and I'm not sure if I expressed this enough, but why glacial loading was so important for freshwater storage in the Great Lakes area is that you had saline water close to the surface. And so if you just had modern topographically driven recharge, you wouldn't flush out that saline water. So it was the loading of the ice sheet that enabled this deep penetration that's now suppressed the salinity, so you have this huge volume of Pleistocene water. Yeah, that's a good question. So we know that some of it's discharged. So a good example is the Saginaw Bay lowlands in Michigan. You still see Pleistocene, so isotopically depleted water that's saline discharging. So you see that in some places. Somebody asked me recently, have I ever done a mass balance calculation of how much salt would have left these basins? I haven't done that, but that's a good question.
You mentioned the possible role of fractures in and the effect of glacial loading on those fractures as far as creating conduits for groundwater flow. And my question is that if you're visualizing the carbonate aquifers as the main recharge into the system, the addition of lots and lots of fresh water implies lots and lots of calcite dissolution. So I wonder, are there also karst features in those carbonate aquifers that have been studied? Is that a significant feature in the system for moving water around?
Yeah, that's a really good question. There are karst in northern Michigan in the carbonates. I haven't seen any studies trying to link that to glacial recharge. There's also some karst features because of the salt dissolution. So I don't know how the timing fits with glaciation, but that's a good question.
What are the conditions that bring about this basal precipitation of calcite glaciers? So on the toe end of glaciers, precipitation of calcite.
Huh. I haven't. I wonder.
So, yeah, I mean, it's wet-based glaciers like this precipitate under the low precipitate calcite.
And is it evenly distributed or localized?
I don't know.
Huh.
But it's a common phenomenon.
Yeah.
So, and it's kind of biological pressure gradient. That's how you go.
Yeah. I don't know.
So with the radiocarbon agents that you have, how do you correct the C13?
Right. So you have to back out calcite dissolution and oxidation of dead organic carbon. So we use the carbon isotope value of DIC in part, but I'm not completely satisfied with that. So that's why I want to couple it with noble gases and hopefully better, test our age corrections. Well, thank you for your attention. I appreciate it.